Good morning, everyone. So today is lecture number 35 of this heat treatment class, and today we're gonna discuss about the nitrating process. Fine. So already you have started a new topic that is on chemical heat treatment of steel, or you can say thermochemical heat treatment of steel, where our main objective is to increase the surface hardness of the steel, right, or the case hardness of the steel. But we have to keep something in mind that the core should be remain tough one, right? So that it can withstand any impact loading, right? But the main objective of to increase the surface hardness is to get wear resistance of the surface or to get high hardness of the surface, because surface will be always exposed to the atmosphere, always exposed to the system, the rotating system or rotating devices, right? So we need a high wear resistant surface. So already we have covered that carburizing part, where we have seen different types of carburizing and what is the difference between them and the processes, and we have solved a numerical how to get the time required for carburizing by the diffusion equation, concentration profile equation, right? So today's topic is nitrating, and where the name suggests we have to use nitrogen atmosphere. So we should need a furnace, and inside the furnace we should have a steel sample where we want to nitrate the steel sample, right? And we need to provide nitrogen gas during the process, right? And the temperature should be a moderate temperature, it should be a high temperature, but the temperature you have to remember is below the temperature required for carburizing, basically. And you have to remember another interesting point here is during nitrating process, we don't want any phase transformation to happen. That means during the nitrating process or just during the cooling stage also, we don't need any phase transformation to happen. Okay, so you can see the menus of today's lecture, that is nitrating, conventional nitrating, and or plasma nitrating or ion nitrating, which is the advanced process, right? We have. Okay, so moving into the introduction part, you can see nitrating. So I already have discussed. So steel will be exposed to a nitrogen atmosphere at high temperature, right? And nitrogen will diffuse onto the surface of the steel. Concentration of nitrogen increases. Basically, here what happens when we heat the steel inside the furnace, which is surrounded by nitrogen, basically, what happens? Nitride formation will take place. Around the surface of the steel, nitride formation will take place. That means the steel surface will form nitrides. It may form iron nitride, it may form alloy nitrides, basically, which improves the hardness or wear resistance of the steel, right? So what will happen? You can see the result of the nitrating, increase the surface hardness of the steel. We can get a surface hardness of, you can see how much hardness we can get, 900 to 1100 VHN. VHN is nothing but, you understand, Vickers hardness number, right? So you can understand how much high hardness value we can obtain. Yes. Sorry?
Brinell hardness.
VHN is what exactly?
Oh, sorry, I thought BHN. Sir.
It's VHN. It's Vickers hardness number, fine. So you can understand how much high hardness we can obtain by doing nitriding only. Because of formation of these alloy nitrides or iron nitrides, we got a very high hardness value, right? So what is the advantage of this? You can see the very good advantage we can obtain here. We can get a steel with good wear resistance, right? And interesting point is we can also get corrosion resistance. This is very interesting. Additional advantage we are getting here. We can increase the corrosion resistance of the surface due to formation of these nitrides. It prevents corrosion somewhat. And the interesting point is hot hardness. Hot hardness, you understand. Suppose you got a steel with this surface is having nitrides, and you want the steel should be work at a high temperature. So even at high temperature, the hardness will not reduce. So that is hot hardness, right? The hardness can be maintained even at high temperature. So this is very interesting. So interesting thing is you get high wear resistance of nitride steel. You will get high hot hardness. That hardness will not reduce at high temperature also, or the strength will not reduce at high temperature. And the corrosion resistance is also good.
This
So
nitrogen atmosphere will be inside the furnace.
sorry, Amiz, can you repeat?
So the atmosphere of nitrogen, will it be inside the furnace? Or
Obviously, if it will be outside the furnace, how nitrating will take place?
so then
Tell me.
how are we providing that atmosphere?
How? Sorry?
How are we providing that atmosphere?
Just by purging nitrogen gas.
And sir, also along with other gases also.
Along with other gases means basically we purge ammonia gas, and this ammonia gas will go into the furnace. It will dissociate. It will dissociate into nitrogen and hydrogen, and finally the nitrogen will basically goes into the
More
steel. Basically, it reacts with the alloying elements present in the steel or with the nitrogen. It will form strong nitrides. Right.
Hello, sir. Can you please add Abhishek Mohanty?
Sorry, I cannot add.
Okay, sir.
Amish, your doubt is clear?
Yes, yes, yes. So we are
Yeah,
adding
you have to
nitrogen
wait.
along.
I am going into the details. I will not skip anything. Right. I'm going into the details of that. You'll get the things soon. So now the question is, which steels are most preferred? If you remember, in the carburizing, we basically prefer low carbon steels, right? Basically, we prefer low carbon steel. Why? Because low carbon steel having ductility somewhat, but where we want to increase the surface hardness only, right? Because we want the core should be tougher one or ductile one, but the surface should be harder one. But here in this case, we need basically a steel which contains those alloying elements which form strong nitrides, because these nitrides will provide you high wear resistance of the surface and high hardness of the surface, right? So basically we choose a medium carbon steel containing certain alloying elements, and those alloying elements when react with the nitrogen atmosphere to form strong nitrides, right? So those alloying elements are basically aluminum is one of the strong nitride former, chromium, vanadium, tungsten, right? Molybdenum. So these alloying elements should be present in the medium carbon steels so that you can form a strong nitride on the surface, right?
सर ଆମର
Yes.
ଯେମିତି ଏଲିଙ୍ଗମ୍ ଡାଇଗ୍ରାମ ଅକ୍ସାଇଡ୍ସ ଆଉ କ୍ଲୋରାଇଡ୍ସ ଏସବୁ ପାଇଁ ଅଛି ନାଇଟ୍ରେଟ୍ସ ପାଇଁ ବି ଅଛି କି?
No, we don't have those kind of diagrams, but still you can obtain data from the literatures easily, which alloying elements will form strong nitrides. Basically, that means those elements have high affinity towards the nitrogen. That's why they form strong nitrides, right? So you can make a diagram if you want. I'm not sure about that, but you can draw a diagram. You can arrange the nitrides according to their stability, according to their according to the reactivity of the element towards nitrides. You can do that. Fine, no problem.
Thank you, sir.
But these are the alloying elements which form strong nitrides. You have to remember, right?
Yes, sir.
So nitrating process. So if you'll go through the process, so already I have written over here in a easy way so that you can easily remember the process. See, whenever you want nitriding process on the steel, the first thing you have to keep into the mind is the steel should be everything should be finished. The last stage will be nitriding. That is the thing. It is not like you will do nitriding, then you do some finishing operation. That means you will give some post heat treatment, or you will give some post grinding or machining. This machining, grinding, and post heat treatment are not preferred after nitriding, or we are not doing that exactly. We have to finish everything before doing nitriding. So that is why the first thing you have to do is what? You should give a proper heat treatment to the steel on which you want to do nitrating. So basically you do what? You do austenitizing and your what? That means you do austenitizing and you do quenching. Basically, we prefer oil quenching, right? That is done, right? So after that, you do tempering of that, but tempering is done at high temperature. You can see 650 degrees centigrade. Then after this is over, we have to do what? We have to do any kind of machining we want. Suppose we want a desirable shape, desirable thickness. So you need to do grinding and machining. So after this is over, then you have to do nitrating. Now the question is how to do nitrating. So after what we need to do, we need to put into the furnace, right? It will be a heat resistance, corrosion resistance, or oxidation resistance furnace, which can withstand very high temperature, or chemicals. So you have to put it into the furnace, then you provide ammonia gas at a high temperature into the furnace. So this ammonia gas will get dissociates and it will release nascent hydrogen and nascent nitrogen, and this nitrogen will start reacting with the surface to form
Sir,
nitrites. Yes.
sir, I guess you missed that coating of tin part.
Yes. I'm supposed to discuss that soon. Don't worry. So suppose, okay. So suppose if you want that your specific surface or specific region of the steel will be exposed to nitrogen, or in that part only you need to do nitrating, other part you don't want, then you can do what? You can do a coating of tin. By doing electroplating, you can do coating of that part only, and this tin plating or this tin coating will prevent the entering of nitrogen into the steel surface, right? So that is the thing. And finally, the nitrating is over. But here the interesting point you have to remember, as I told, there will be no phase transformation. So nitrating is carried out at a temperature of, you can see it is written 590. It is, I missed maybe. Okay, I'll show you in the next slide. It is there, 590 degrees centigrade. So nitrating is carried out at a temperature of 590 degrees centigrade. That means you understand it is below austenitizing temperature. So there will be no phase transformation involved here. And finally, after nitrating over, the steel will be cooled inside the furnace by supplying this ammonia gas only. Fine. So what are the parameters? You can see the parameter is, as I told, nitrating temperature is 590 degrees centigrade, which is in the ferrite region of the steel. Here there will be no phase transformation involved. And you can see ammonia gas temperature is 550 degrees centigrade. That means at this temperature, ammonia gas will be supplied, but it will break down into nascent nitrogen and hydrogen. And if you look into the temperature treatment time, nitrating time, it is very high compared to that of carburizing, nearly to the 100 hours. It depends upon the depth of how much depth you want. 21 hours to 100 hours. But in case of carburizing, if you remember, it is very small time. It is hardly 7 hours, right? Or for a gas carburizing, it is very less. Now, there is a very interesting issue which we get in the conventional nitrating. So till now, we were discussing about the conventional nitrating. This conventional nitrating have some problem associated with that. What is the problem? See, while we are doing nitrating, after the end of the nitrating, we get a white layer on the surface of the steel. That white layer is basically a particular compound. That is a compound of iron and nitrogen. That is iron nitrate. Those are basically gamma prime nitrates and epsilon nitrates. Fe4n and Fe2n. Right. So these white layers, these iron nitrate layers, these gamma prime iron nitride and gamma prime gamma prime and epsilon gamma iron nitride, they are basically very brittle. See, we want a high hardness, but we don't want any brittleness, basically. So due to formation of these iron nitrides, the brittleness increase on the surface. So this white layer should be removed before putting the steel into the service, right? So you can do mechanical you can polish it and you can remove that surface, but it is not an easy job. So we try to prevent. So our aim is to prevent this formation of iron nitrides, basically, Fe4n and Fe2n. So the solution is, we have two solutions. We'll discuss that. How to suppress white layer formation. So we have two processes. One is Floy process, which is double stage nitrating process. That means this process, you understand, we have to do nitrating in two stages. That's why it is called double stage nitrating. We have different parameters. In first stage, we have different parameters. In second stage, we have different parameters. And we can suppress the white layer formation. And the plasma nitrating, it is a very new process, basically. That means these days we are preferring this kind of process, which is a very fast, efficient process. And also we do not have any white layer formation, basically. Or you can suppress the formation of white layer. Let me tell you one interesting point here is this, basically this white layer, which is iron nitride, which formed due to high nitrogen potential. So carefully we have to do nitriding at a low nitrogen potential. If the nitrogen potential can be controlled, we can control the formation of iron nitride. Or this white layer formation can be suppressed. So Floy process.
Yes, sir.
Sorry. Yes.
Sir, if low nitrogen potential is maintained, that Fe4n and Fe2n will not form.
Yes, that is our main criteria.
Sir,
We have to
then
control
in that condition, what compound will form?
alloy
I
nitrides,
mean,
basically. See, we want,
okay, sir.
already I have told you that we prefer those kind of steel which contain alloying elements which are strong nitrate formers, right? That means already those alloying elements have high affinity to the nitrogen compared to that of iron. So if you maintain a low nitrogen potential, even then those alloy nitrates will form, but iron nitride will not form. Iron nitride formation will be suppressed. But if you maintain a high nitrogen potential, what will happen? These alloy nitrates will form, and these iron nitrates will also form due to high nitrogen.
Sir, how much area is occupied by the alloys in the surface? I think that is very
How
low.
much area you can? This is in the atomic level. How you can tell that? You have added alloying elements. These alloying elements are basically substitutional alloying elements. So it depends upon the how much amount of alloying element are present in. Suppose 1% chromium is there, or it may be 2% chromium, or suppose you are adding 0.5% aluminum. So in that you can tell, right? In the atomic level, it is okay.
Okay, sir.
It is not like half portion is covered by aluminum and half portion is covered by iron only. You cannot tell like that. It is in the atomic level, right? Alloying elements
Yes,
should
sir.
be uniformly distributed. That is the point. Where there is alloying element, that will form alloy nitrides. Is it okay? Or yeah, you have any question, you can ask. No problem.
Okay, sir. Okay, sir.
You understood my point? It is in the atomic level.
Yes, sir.
Atoms are distributed in the atomic level. The aluminum will occupy the iron sites. The chromium will occupy the iron sites, because these are substitutional alloying elements. Anyway, so okay, we'll discuss about the Floy process, which is a double stage nitrating process. Already I have told, since this is a double stage nitrating process, so you should keep this in mind, that the parameters in the first stage and second stage will be different. Parameters means in terms of nitrogen potential I am talking about, and in terms of temperature also. Okay, now I'm going to throw a question to you. Let me see how you can use your mind. Since the atmosphere is not only nitrogen, we have hydrogen and nitrogen. So can you people tell me, I will give you, okay, I will give you 1 minute. This is sufficient time. So now the time starts. Can you tell me if you want to maintain a how you can maintain a high nitrogen potential, how you can maintain a low nitrogen potential? The hint is you are supplying ammonia gas, which will be decomposed into nitrogen and hydrogen, or you can provide a mixture of nitrogen and hydrogen directly into the atmosphere. So question is how you can maintain a high nitrogen potential, how you can maintain a low nitrogen potential.
In high temperature, ammonia will dissociate. So nitrogen will be there in more, and in normal temperature, nitrogen and hydrogen will react to each other to form ammonia.
Amish, can you repeat again? First question is how you can maintain a high nitrogen potential.
But in high temperature, ammonia will dissociate, forming nitrogen.
Okay, fine.
And so in normal temperature, nitrogen and hydrogen will react to with each other to form ammonia. Nitrogen content will be decreased.
So that means your point is if you maintain a high temperature, then you can maintain a high nitrogen potential. That is the thing.
Yes, sir, temperature.
Okay. Anybody want to speak anything else? I have also told you that you can provide both mixture of nitrogen and hydrogen, or you can provide ammonia gas also. And ammonia gas is provided at a definite temperature.
Sir, we can control the pressure.
You can control the pressure. Okay. See, nitrogen potential, this simply means how you can say potential. It is a gas, right? So if you maintain a high partial pressure of nitrogen, that means it is having high nitrogen potential. If the partial pressure of nitrogen will be less, so it is a low nitrogen potential. It is okay? So potential in terms of, I'm talking about the partial pressure of that particular individual gas. It is okay. You people understood my point?
Yes, sir.
Suppose I am talking about I have to maintain a high carbon potential during carburizing. So what it means? The partial pressure of carbon monoxide should be high. You understand my point? Okay, let me show you the slides. You can get the answer from here. So two-stage nitrating, which is a flow process. You can see in the first stage nitrating. Okay, in the first stage nitrating, which is carried out at low temperature. You can see the temperature is 495 to 525 degree centigrade. With high nitrogen potential. So, Amish, do you think the answer is right, which you have told?
Not getting, sir. What is high nitrogen?
Okay, the first stage of nitrating is done at a low temperature, which is 495 degrees centigrade to 525 degrees centigrade. So this is the parameter, temperature parameter in the first stage nitrating. But here we maintain high nitrogen potential. How? 20% dissociated ammonia will be there. So what happens if the nitrogen potential is high in the first stage, the temperature is low, but here what happens? The first growth of nitrate case will be taking place. So here in this stage, we will form iron nitrites. That is epsilon iron nitrate will form, and your gamma prime nitrites will form. Fe4n and Fe. This epsilon nitride is Fe2n, and this gamma prime nitride is Fe4n, basically. So in the second stage, what we do, you can see in the second stage, which is carried out at high temperature, 550 degrees centigrade to 565 degrees centigrade. Right? We cannot go to a very high temperature. Always I told, we are not doing this nitrating at a high temperature, very high temperature in the austenitizing region. We are doing nitrating in the ferrite region, basically. And you can see the atmosphere of low nitrogen potential. So this is which is 80% dissociated ammonia. And in the second stage, the white layer, which is iron nitrate, get dissociates and get eliminated. Right? This leads to the increase in the depth. So nitrate depth will be increased, but the hardness will be reduced. Right? So the conclusion is what? The conclusion is in the flow process, we are doing nitrating in two stages. The first stage we are maintaining low temperature, but we are maintaining high nitrogen potential. Fine. So that iron nitrate will form, and we can get a strong nitrate forming case, right? But in the second stage, we are doing nitrating at high temperature so that this iron nitrate will decompose or it will get eliminated by maintaining a low nitrogen potential here. Fine. I think you don't have any confusion right now. So can you tell me right now the answer of this question which I have asked? Latmika, can you answer?
सर ଯଦି 80% dissociate होची सर मोटी डाउट अछि.
My question was how you can maintain a high nitrogen potential and how you can maintain low nitrogen potential.
सर मोटी की डाउट अछि.
Okay, Pranav, you want to speak anything?
Sir, it is 80% means basic nitrogen produce होची ना, ammonia basic dissociate होची.
Okay.
କିନ୍ତୁ
Jivajyoti?
ମାନେ low pressure maintain କରା ଉଚିତ ରେ.
Jivajyoti?
Yes, sir. Yes, sir.
Can you answer how to maintain high nitrogen potential and low nitrogen?
No,
Okay, Rutuparna, you want to speak something about this?
Sir, if there will be high partial pressure, then there will be high nitrogen potential, and
Very
low
good. Yes.
partial pressure, then there will be low nitrogen potential.
So now you have to justify how high nitrogen potential, high partial pressure and low pressure of nitrogen. Already it is written 20% dissociated and 80% dissociated. So more dissociation, more nitrogen, right? Less dissociation, less nitrogen. Now you people are getting my point? But here the thing is what? Hydrogen is also there. Two gases are there, right? More hydrogen will be there means nitrogen potential, partial pressure will be reduced. That is another point. If we have only single gas, there is no problem. But if we have a two gas, then partial pressure, individual partial pressure will be also dependent upon the another gas phase also, right?
Sir,
Anyway,
you said if there will be more dissociation, then there will be more nitrogen potential.
see, if more dissociation will be happening, that means more nitrogen and hydrogen will come out. But the point is what? Hydrogen is also there. Or no, if only nitrogen will be there, then that is fine. But here two gases are there. So we don't want more dissociation to happen. If more dissociation will be happening, more hydrogen gas will be also coming out. Nascent hydrogen will be available. So partial pressure will be less for the nitrogen here. So we have a low nitrogen potential if more dissociation will happen. If less dissociation will be happen, then less amount of nitrogen, less amount of hydrogen will be there. And we want nitrogen should react basically, right? And nitrogen have affinity towards these alloying elements. So if less dissociation will happen, you can say you have good nitrogen potential here. Now it is clear?
Yes, sir.
Sir, partial pressure is directly proportional to mole fraction, no?
Yes, mole fraction, but you have to look into the atmosphere, total atmosphere of the furnace now. It is okay?
Okay, sir.
Because two gases phase are involved here. That means hydrogen is also interacting with the surface. Where hydrogen will go? You tell me. If two gases phase will be there, both will interact or not? Can you tell me?
Yes, sir.
But if two gases phase are there, both are interacting with the surface, and you want only one single gas should react, then what will happen? The efficiency of interaction by nitrogen will be reduced or not?
Sir, again, please.
If two gases phase will be present, both are interacting with the surface of the steel, then efficiency of interaction of nitrogen will be reduced or more?
It will be reduced.
Obviously reduced. If only nitrogen will be there, then efficiency will be more. Only nitrogen will interact. Now, I think your points are clear, right?
Yes, sir. Yes, sir.
Okay, anyways. So now last topic is plasma nitriding, which is the advanced process. Plasma nitriding is also called ion nitriding because here ions are involved. Here the ions are involved. Okay. Here ions are involved. So this is a fast and effective process. You can see an efficient process than conventional route. And you can see there is interesting point during nitriding, this plasma nitriding or this ion nitriding, a glow covers the sample always, also called glow discharge process. The plasma nitriding, ion nitriding is also called glow discharge process. This glowing of the glowing is due to the presence of this nitrogen ions. Because this nitrogen ions is covering the steel, which looks like a glowing surface. During the process of plasma nitriding, the sample will appear is glowing because a glowing atmosphere will be there, or atmosphere of nitrogen ions will be there, which appears as a glowing surface. So you basically, to understand, ionization is taking place here, right? And this nitrogen ion is getting bombarded to the surface of the steel, right? And it's a very fast process, efficient process. And you can see this plasma nitriding is carried out at a very low pressure. That means you have to need a chamber, or you need a furnace which is can be done vacuum. A vacuum chamber will be there. The gas will be remain in excited state, right? The temperature is basically 450 to 550 degrees centigrade. Okay. Now, if you look into the unit of plasma nitriding, unit means I am talking about the setup, complete setup of the plasma nitriding. You can see what we have. We have, this is the setup for the plasma nitriding. So this is the main furnace or main chamber which we need to vacuum. And this is the steels. This is the steel which is inside the chamber, vacuum chamber, right? And we have electrodes, you can see. So this is negative electrode, this is positive electrode. Positive electrode is attached to the chamber itself. That means the anode is the chamber itself, vacuum chamber or the vacuum furnace chamber, right? And cathode is what? Cathode is attached to the sample, which we need to be nitride, or nitriding will taking place, right? And they are connected to the supply. Supply is here. You can see supply, electricity supply or voltage supply, and we have a control unit, microprocessor control unit, which can control the temperature, which can control the voltage, which can control the vacuum level inside the furnace. And we need a gas purging system. Sorry, gas purging means gas pumping system, which will provide mixture of nitrogen and hydrogen into the chamber. And we need a pumping system, as I told. This is the workpiece, and we need a gas mixing device. Already the gas will be mixed, nitrogen and hydrogen will be mixed in definite proportion, and it will be purged into the furnace. And due to high voltage, when the voltage will be very high, like 1000 voltage, like that, ionization will take place. Nitrogen will get ionized, and it will get bombarded onto the surface of the steel, and that will lead to the nitriding process. Here it is written something. I have written here. So this is all about your nitriding. So I will end the topic here. We'll continue our lecture in the next class.
Hello, sir.